Okay, today we're going to look at the relativistic energy and momentum equation. We're going to try to derive it. So let's start off with the total energy squared minus PC squared. Let's see how we can contort this, these two terms here. The total energy, of course, is a relativistic mass times speed of light squared. This is the total energy. The momentum, of course, is mv, where m again is the relativistic mass. So we'll plug those two into here. And here they are. The only difference is that m, remember, I have another lecture called the relativistic mass where I derive this equation. Relativistic mass equals the rest mass divided by the square root of 1 minus velocity squared divided by the speed of light squared. So we're going to plug that into the two m's here, and then plug those two into these two right here. So this will become that, this will become that, according to these equations right here, and this equation right here. This is going to be just a lot of algebra. Decided to do it for you guys. So square everybody in here, you'll get this. Square everybody in here, you'll get this. Go ahead and pull out the m squared c to the fourth out of pull out m squared c squared out of these two terms. You'll get the m squared and c squared. This is c to the fourth because of something I'm about to do in just a second. And so you'll get c squared minus v squared is this term right here. What I decided to do is do two algebraic steps. I decided to multiply the top and bottom by c squared. So both bottoms are the same. So c squared times this, there'll be just 1 here if we add the two fractions. If you multiply this through by c squared, you'll get c squared minus v squared. There's a c squared minus v squared. And if you multiply the top by c squared, right here when I pulled out the c squared, and now we had a c squared, then we factored out. If you multiply that by c squared, of course, because we have to multiply the top and bottom of this by c squared, you'll get c to the fourth. Okay. I believe me. Well, you can prove to yourself that this is algebraically equivalent to this. If you want, you can do it out. Okay. If we just notice, we'll cancel those two, of course, and we'll be left with m0 squared c to the fourth. That's what we got right here. And so we'll notice that our original thing, therefore, is e squared minus pc squared. That I wrote right there. And we had transformed that into this, which means this is equal to this. And so this is equal to this right here. I just rewrote it as m0 c squared squared. That's the same as this. So this, we transformed into this, which means this is equal to this. Okay? And m0 c squared, of course, is the rest energy. All right? So there is our relativistic momentum equation. And I want you to make sure that you do not mistake this for the other energy equation, which does not have momentum. It has kinetic energy. And that's that the total energy is equal to, this is a relativistic equation. The total energy is equal to the kinetic energy plus the rest energy. And then I just threw this in as a bonus. The momentum times the speed of light squared equals the total energy times the velocity, in case you might want to use that. Okay, I hope you enjoyed this lecture. I look forward to any comments at the bottom. Thank you very much.